Welcome to Sleep Lab, where we unlock the universe's most mind-bending secrets and transform them into mesmerizing journeys through space and time. I'm your host, and tonight, we're about to embark on the most impossible story ever told. A story so incredible that if it were fiction, you'd say it was too far-fetched to believe. Picture this. 4.6 billion years ago, you didn't exist. Earth didn't exist. The very atoms that make up your body were scattered across the cold, empty void of space. Yet somehow, through a series of cosmic accidents so unlikely they border on the miraculous, that stardust became you. This is the ultimate underdog story, the tale of how literally nothing became everything, how cosmic dust became oceans, how violent collisions became the moon that lights your nights, how hellish bombardments became the protective atmosphere you breathe. This isn't just geology or astronomy. This is the biography of reality itself, written in stone, ice, and starlight. So dim the lights, settle into the cosmic theater of your imagination, and prepare to witness the most spectacular transformation in the known universe. Tonight, we're traveling back to the very beginning, to watch our planet being born from chaos, surviving catastrophes that would make Hollywood disasters look like gentle summer rain, and ultimately becoming the only known cradle of life in an otherwise sterile cosmos. Welcome to the greatest story never told in its entirety, the 4.6 billion-year epic of how Earth defied impossible odds to become your home. Let's journey through deep time together. Welcome to the most mind-bending story in the universe, the tale of how cosmic dust became you. Right now, you're sitting on a planet that mathematically shouldn't exist. Yet here we are, about to uncover the extraordinary sequence of cosmic accidents that made your existence possible. Our journey begins 4.6 billion years ago in what appears to be absolutely nothing, a region of our galaxy containing only the thinnest whisper of matter scattered across dozens of light years. This stellar nursery, called the solar nebula, was so diffuse that its density was lower than the best vacuum we can create in laboratories today. But within this apparent emptiness lay every atom that would eventually become our solar system. The cloud was dominated by hydrogen and helium left over from the Big Bang. But scattered throughout this primordial mixture were heavier elements with the most incredible origin story imaginable. Every carbon atom in your DNA, every oxygen molecule you breathe, every iron atom flowing through your bloodstream. All of these were forged in the nuclear furnaces of massive stars that lived, died, and exploded as supernovae across billions of years. You're quite literally made of star stuff, and 4.6 billion years ago, this stellar dust was floating peacefully through space, waiting for the perfect trigger to begin its transformation into planets, life, and ultimately you. That trigger came from one of the most violent events in the cosmos, a nearby supernova explosion. When a star 8 times more massive than our Sun reaches the end of its life, it doesn't fade quietly into the night. Instead, it explodes with the force of billions of atomic bombs, detonating every second for weeks, releasing more energy in those few weeks than our Sun will produce in its entire 10 billion-year lifetime. The shock wave from this cosmic detonation traveled through space at thousands of kilometers per second, carrying with it not just tremendous energy, but also the heavy elements synthesized in the star's final moments. When this shock wave reached our peaceful nebula, it compressed the gas and dust like an enormous invisible hand squeezing a cosmic sponge. The compression wasn't uniform. Some regions became denser than others due to random fluctuations, and in these denser pockets, something remarkable began to happen. For the first time in millions of years, gravity began to overcome the thermal pressure that had kept the cloud dispersed. What had been a stable, static cloud began to contract under its own weight, and once gravitational collapse begins, it becomes an unstoppable force of cosmic construction. As the collapse progressed over hundreds of thousands of years, something beautiful happened that follows the same physics that makes figure skaters spin faster when they pull their arms inward. Conservation of angular momentum accelerated the cloud's rotation, and the combination of contraction and rotation created a flattened, spinning disk, with most of the mass concentrated at the center, where our proto-sun was taking shape. But surrounding this nascent star was a vast rotating disk of cooler material extending billions of kilometers, the construction site where all the planets would be built. Temperature gradients across this disk created cosmic zoning laws that would determine what kinds of worlds could form where. Close to the hot proto-sun, only materials with high melting points, metals and rocky minerals, could condense into solid particles. Further out, where temperatures were cooler, volatile compounds like water, methane, and ammonia could freeze into solid ices. This chemical segregation would prove crucial for determining the compositions of different planets. The transformation from microscopic dust to planet-building material began through electrostatic forces so gentle they seem almost magical. Dust grains floating in the disk started sticking together like cosmic lint, creating aggregates held together by forces weaker than a butterfly's touch. These initial clumps were incredibly fragile affairs that could be shattered by the gentlest collision. Yet somehow, in the chaos of the spinning disk with particles swirling at several kilometers per second, these delicate structures not only survived but grew larger. The secret was that not all collisions were destructive. At just the right velocities and angles, particles could stick together rather than shatter, gradually building larger and larger aggregates through a process that required extraordinary cosmic precision. Once these clumps reached sizes of roughly a kilometer across, their own gravity, though extraordinarily weak, began to play a role in attracting additional material. In the vast expanse of the disk and over timescales of millions of years, even the gentlest gravitational forces could accumulate enormous effects, creating larger objects that could attract even more material in an accelerating process of cosmic construction. Every atom in your body participated in this incredible construction project, forged in stellar interiors, delivered by supernova shockwaves, condensed in the cold of the protoplanetary disk, and assembled through billions of years of gravitational attraction into the world we call home. Now we enter one of nature's most elegant demonstrations of exponential growth, the cosmic snowball effect that transformed kilometer-sized pebbles into planet-sized worlds in what amounts to a cosmic eye blink. Once planetesimals reached that critical size of about a kilometer across, physics took over with a vengeance, creating what scientists call runaway accretion, a process so efficient it could build planets from pebbles in less than 100,000 years, which is essentially instantaneous in astronomical terms. Here's where the mathematics of gravity becomes absolutely beautiful in its simplicity and power. As planetesimals grew larger, their gravitational pull increased proportionally to their mass, but their ability to capture other objects increased even more dramatically due to a phenomenon called gravitational focusing. When a small object approaches a larger one in space, the gravitational field of the larger object can bend the trajectory of the smaller one, effectively increasing the target area for collision far beyond what simple geometry would predict. It's like having a cosmic vacuum cleaner whose suction radius grows stronger and wider with every piece of debris it collects. Once this runaway process began in earnest, the growth rates became absolutely staggering. A planetesimal that managed to reach 1 kilometer in diameter could grow to 100 kilometers across in less than 100,000 years, an eye blink in astronomical terms that represents one of the most dramatic examples of exponential growth in the natural world. Each collision not only added mass to the growing object, but also increased its gravitational influence, allowing it to perturb the orbits of nearby planetesimals and draw them into collision courses through a positive feedback loop that concentrated more and more material into fewer and fewer large bodies. The early solar system during this period would have been the most spectacular construction zone in the galaxy, filled with thousands of growing planetesimals ranging in size from small mountains to objects approaching the dimensions of Earth's moon. These bodies moved in complex evolving orbits around the young sun, their paths constantly perturbed by gravitational interactions with their neighbors in a cosmic dance of creation that was both chaotic and precisely orchestrated by the laws of physics. As the largest objects grew more massive, something fundamental changed in the dynamics of the system. They began to stir up the orbital motions of smaller bodies, increasing collision velocities beyond their mutual escape velocities. What had been relatively gentle, sticking together, became increasingly violent, smashing apart, marking the transition from runaway growth to what scientists call oligarchic growth, where only the largest embryos could continue growing efficiently, while smaller objects found their growth stunted by the increasingly violent collision environment. During this oligarchic phase, Mars-sized planetary embryos emerged as the dominant players, each controlling its own feeding zone and maintaining orbital separations that prevented them from immediately colliding with one another. These embryos maintained separations of at least 5 Hill radii, the distance within which an object's gravity dominates over the Sun's tidal effects. Through a complex dance of gravitational repulsion and orbital adjustment that created a solar system populated by several dozen planetary embryos, the efficiency of this accretion process depended critically on the size distribution of planetesimals in the disk, with recent research revealing that the formation of different types of planets was favored by different planetesimal sizes. Giant planets were built most efficiently through the accretion of small planetesimals whose random velocities could be damped by gas drag from the nebula, while larger planetesimals, once stirred to high velocities, became more likely to fragment than stick together upon collision. As these embryos grew more massive, they began to experience significant heating from the tremendous energy released during impacts. Collision velocities reached several kilometers per second, with each impact releasing energy equivalent to massive nuclear explosions. The cumulative effect of countless impacts was to transform cold, solid planetesimals into increasingly hot, partially molten planetary embryos, with objects approaching Mars size experiencing impacts energetic enough to create global magma oceans that fundamentally altered their internal structure through differentiation. By the end of the oligarchic growth phase, our solar system contained approximately 50 to 100 planetary embryos, with masses ranging from that of Earth's moon to that of Mars, embedded within a swarm of smaller planetesimals that had escaped accretion. This population represented the raw material for the final phase of terrestrial planet formation, setting the stage for the giant collisions that would ultimately create Earth, Venus, Mars, and Mercury through a process of mutual gravitational perturbation and collision. The transformation from cosmic dust to planetary embryos represents one of the most remarkable examples of self-organization in nature, where simple physical forces operating over vast timescales created the complex, hierarchical structure that characterizes planetary systems throughout the universe. Prepare yourself for the most catastrophic and defining moment in Earth's entire history. A collision so violent and transformative that it fundamentally altered our planet's destiny and created the Moon in a single devastating impact. This wasn't just another planetesimal collision. This was planetary catastrophe on a scale that challenges human comprehension, representing the moment when cosmic destruction became cosmic creation in the most dramatic way possible. Meet Theia, named after the Greek Titaness who gave birth to the moon goddess Selene. This Mars-sized world, roughly half the mass of present-day Earth, formed in one of Earth's Lagrange points, those gravitationally stable regions located 60 degrees ahead of or behind Earth in its orbit around the Sun. For millions of years, Theia grew quietly in this cosmic safe harbor, accumulating mass while protected from the gravitational chaos that characterized the inner solar system during the final stages of planetary formation. These Lagrange points function like cosmic parking spaces, where smaller objects can temporarily hide from the gravitational perturbations of larger bodies. But there's a fundamental problem with this arrangement. They're only stable for objects much smaller than planets. As Theia reached roughly half Earth's mass and the solar nebula began to dissipate, removing the damping effects of gas drag that had helped maintain orbital stability, the gravitational balance became increasingly precarious. The destabilization of Theia's orbit likely resulted from a complex interplay of factors, including Jupiter's migration through the outer solar system, the dispersal of the solar nebula, and gravitational perturbations from other large embryos in the inner solar system. As Theia's orbit became unstable, It began a slow spiral toward an inevitable collision with Earth, a death dance that may have taken hundreds of thousands of years as the two bodies' orbits gradually synchronized through repeated close encounters that exchanged orbital energy and angular momentum. The mathematics of orbital mechanics dictated that this collision would not be a head-on impact, but rather an oblique strike, with Theia approaching Earth at an angle of approximately 45 degrees and a velocity of around 4 kilometers per second, roughly 10 times faster than a rifle bullet. The combined kinetic energy of this collision was equivalent to about 100 million times the energy that would later be released by the asteroid impact that killed the dinosaurs, or roughly equal to the gravitational binding energy of the entire Earth. When Theia struck Earth, this staggering amount of energy was released in a matter of hours, instantly vaporizing thousands of cubic kilometers of rock and metal, while generating temperatures exceeding 8,000 Kelvin, hotter than the surface of the Sun. The impact created a massive crater that temporarily deformed Earth's shape, sending shock waves reverberating through the planet's interior like a cosmic bell struck by an unimaginably powerful hammer, while ejecting enormous quantities of material into space at velocities exceeding Earth's escape velocity. The immediate aftermath transformed Earth into something resembling a small star more than a planet, with the entire surface covered by a magma ocean hundreds of kilometers deep that glowed white-hot from the thermal energy released by the impact. This global ocean of molten rock represented the complete melting of Earth's mantle and much of its crust, creating a homogeneous mixture of silicate minerals that would later differentiate into the layered structure we see today. The formation of the Moon from the debris created by this collision represents one of the most elegant examples of cosmic recycling, where destruction and creation occurred simultaneously on a planetary scale. The impact ejected approximately 2 Earth masses of material into space, but not all of this material escaped Earth's gravitational influence. The fraction that remained bound formed a complex disk of vapor, liquid droplets, and solid fragments extending from just above Earth's surface to beyond the Roche limit. Within this impact-generated disk, the same processes that had earlier built planets from the solar nebula began operating on a smaller scale, with collisions and gravitational attraction gradually assembling the scattered debris into larger and larger clumps. The accretion of the Moon occurred with remarkable speed compared to the formation of the original planets, taking perhaps only a few thousand years for the bulk of the debris to coalesce into a single satellite. The newly formed Moon was initially much closer to Earth than it is today, orbiting at a distance of only about 15,000 kilometers, less than half the diameter of Earth itself, and appearing roughly 20 times larger in the sky than it does today. At this close distance, the Moon raised enormous tides on Earth's still molten surface, creating bulges of liquid rock hundreds of meters high that swept around the planet every few hours as the Moon completed its rapid orbit. The gravitational effects of the giant impact fundamentally altered Earth's rotational characteristics in ways that would prove crucial for the eventual development of life. The collision transferred enormous amounts of angular momentum to Earth, spinning it up to rotate once every 5 to 6 hours, rather than the 24-hour day we experience today. More importantly, the impact tilted Earth's rotational axis by approximately 23.5 degrees relative to its orbital plane, creating the obliquity that gives rise to seasonal variations in solar heating across Earth's surface. The geochemical evidence for this dramatic origin story has accumulated over decades of studying lunar samples returned by the Apollo missions, providing compelling support through isotopic analysis that reveals the intimate connection between Earth and Moon. The most striking evidence comes from oxygen isotopes, which show virtually identical compositions between Earth and lunar rocks, a relationship that would be extremely unlikely if the Moon had formed elsewhere in the solar system and been captured by Earth's gravity. The moon birth catastrophe thus represents far more than simply the formation of Earth's satellite. It was the transformative event that reset nearly every aspect of our planet's physical and chemical evolution, establishing the planet's rotational characteristics that govern climate and day length, creating the Moon, whose gravitational influence stabilizes Earth's obliquity and drives ocean tides, and generating the thermal energy that would power geological activity for hundreds of millions of years. This single event, lasting only hours but requiring billions of years of prior planetary evolution to set the stage, exemplifies how the most dramatic and unlikely occurrences can prove essential for creating the conditions necessary for life. Welcome to hell. For the next 500 million years, Earth would be more like Venus than the blue marble we know today. A world where water could exist only as superheated steam, where surface temperatures could melt lead, and where the very air was composed of vaporized rock. This was the Hadean Eon, named after Hades itself, and somehow our planet had to transform from this hellscape into something capable of supporting the chemistry of life. The magma ocean created by the moon-forming impact extended hundreds of kilometers deep throughout Earth's mantle, with surface temperatures exceeding 2000 Kelvin and an atmosphere that consisted primarily of vaporized rock and superheated steam. This wasn't a static pool of molten material, but rather a dynamic convecting system where superheated rock rose from the depths while cooler material sank, creating planet-wide circulation patterns that would continue for millions of years as Earth slowly attempted to cool and solidify. The atmosphere during this period was unlike anything in our solar system today, a dense, opaque envelope of silicate vapors and metallic gases that completely blocked visible light while trapping thermal radiation and slowing the cooling process significantly. This atmospheric blanket of vaporized rock created an intense greenhouse effect that maintained hellish surface conditions long after the initial impact energy should have dissipated into space. As the uppermost layers of the magma ocean began to cool, the first attempts at crust formation occurred through the crystallization of high-temperature minerals like olivine, pyroxene, and plagioclase feldspar. These minerals separated according to their densities and chemical affinities, with the lightest components floating to the surface to form a thin, unstable skin of solid rock over the molten interior. However, this primordial crust was extraordinary, wryly fragile and short-lived due to the continued bombardment that would characterize Earth's early history. The late heavy bombardment, occurring approximately 4.1 to 3.8 billion years ago, represented one of the most cataclysmic periods in Earth's history, when our planet experienced roughly 22,000 impacts capable of creating craters larger than 20 kilometers in diameter, plus about 40 massive impacts that created basins over 1,000 kilometers across. Each major impact not only shattered and vaporized the newly formed crust, but also added tremendous amounts of kinetic energy to the planet, remelting large portions of the surface and essentially resetting the cooling process time and time again. This bombardment was triggered by a grand reorganization of the outer solar system, as the giant planets Jupiter, Saturn, Uranus, and Neptune underwent orbital migrations that destabilized the asteroid belt and scattered countless rocky and icy objects throughout the inner solar system like cosmic billiard balls. The planet was caught in a seemingly endless cycle of attempted solidification, followed by impact-induced remelting, with each major collision threatening to return Earth to its immediate post-impact molten state. Yet paradoxically, this destructive bombardment was simultaneously delivering the water and organic compounds that would eventually make life possible. Each comet that struck Earth brought with it significant quantities of water ice, carbon dioxide, and other volatile compounds that had been frozen in the cold outer regions of the solar system during its formation. When these icy projectiles collided with Earth's hot surface, they instantly vaporized, adding their volatile contents to the planet's growing atmosphere and beginning the long process of atmospheric evolution that would eventually create conditions suitable for liquid water. Volcanic outgassing played an increasingly important role as the planet's interior began to differentiate and the first volcanic processes became active on the cooling surface. Unlike modern volcanic eruptions, which release gases that have been processed through various crustal and atmospheric cycles, the early volcanic outgassing represented the first release of gases that had been trapped within Earth's interior since the planet's formation. These primordial volcanic emissions were dominated by water vapor, constituting approximately 80% by volume, along with carbon dioxide, sulfur dioxide, nitrogen, and smaller amounts of hydrogen and other gases. The gradual cooling of Earth's surface and the eventual condensation of water vapor to form the first liquid oceans represented a critical threshold in planetary evolution, marking the transition from a completely inhospitable world to one where more complex chemical processes could begin to operate. The condensation process occurred gradually as surface temperatures dropped below the critical point of water, allowing the first liquid droplets to form in the cooler regions of the planet and gradually coalesce into larger bodies of water. These early oceans were vastly different from modern seawater, being highly acidic due to large quantities of sulfur dioxide and other volcanic gases dissolved in them, and containing much higher concentrations of dissolved metals and other compounds leached from the newly formed crustal rocks. The establishment of a stable crust required multiple cycles of melting, cooling, and solidification before a permanent solid surface could be maintained, with each major impact destroying existing crustal formations, but gradually declining bombardment intensity, allowing for more substantial crustal development. The thermal evolution of Earth during this period was governed by the complex interplay between heat sources and heat loss mechanisms, with the planet's internal temperature slowly declining as radioactive decay rates decreased and the efficiency of heat transfer to the surface improved. The early Earth contained much higher concentrations of short-lived radioactive isotopes than exist today, particularly aluminum-26 and iron-60, which generated enormous amounts of internal heat during their rapid decay and helped drive the vigorous convective processes that facilitated Earth's differentiation into its layered structure. The transformation from Hell Planet to a world capable of supporting geological and eventually biological processes represents one of the most remarkable transitions in planetary science, demonstrating how the most extreme and violent conditions can ultimately give rise to stable, habitable environments. The gradual cooling and solidification of Earth's surface during the late Hadean Eon set the stage for all subsequent planetary evolution, establishing the fundamental physical and chemical frameworks within which plate tectonics, ocean chemistry, and atmospheric dynamics would later operate. Hidden beneath Earth's cooling surface, the most profound transformation in our planet's history was about to begin. The iron catastrophe, a runaway process that would completely reorganize Earth's interior and create the magnetic field that protects us today. Without this dramatic separation of iron from rock, Earth would be a dead world like Mars, its atmosphere stripped away by solar winds, incapable of sustaining the magnetic shield that makes life possible. The stage was set by accumulating radioactive heat deep within Earth's interior. The early Earth contained far more radioactive isotopes than exist today. Aluminum-26, iron-60, potassium, uranium, and thorium generated enormous amounts of internal heat through radioactive decay, gradually raising Earth's interior temperature toward a critical threshold that would trigger one of the most important events in planetary evolution. At approximately 1200 to 1500 degrees Celsius, depending on pressure and composition, something extraordinary happened that would reshape our entire planet. Iron-nickel alloys began to melt, while silicate rocks could remain solid, or only partially molten. This temperature difference was the key that would unlock Earth's transformation from a relatively homogeneous mixture of rock and metal into the highly differentiated world we know today. Here's where physics takes over with beautiful, inexorable simplicity. Iron has a density of 7.9 grams per cubic centimeter, nickel 8.9 grams per cubic centimeter, while silicate minerals typically range from 2.5 to 4.0 grams per cubic centimeter. When iron melts, it becomes a liquid roughly twice as dense as the surrounding solid rock, and density differences in a gravitational field create one of nature's most powerful driving forces. The iron catastrophe began when the first drops of liquid metal started to sink toward Earth's center, but this wasn't just gravity acting on a few drops of molten iron. It triggered a runaway process that would reshape the entire planet within 30 to 100 million years through a positive feedback mechanism that transformed what might have been gradual segregation into a planetary-scale avalanche of reorganization. As iron began to sink toward the center, the gravitational potential energy released by this downward movement was converted to heat through friction and compression, further raising the internal temperature and accelerating the melting and migration of additional iron. Every meter that iron descended released gravitational energy that converted to heat, which accelerated more melting, which caused more iron to sink, creating more heat in an exponential process that drove the system toward complete differentiation with extraordinary efficiency. Iron segregation operated through three distinct mechanisms, working simultaneously throughout the planet's interior. In regions where temperatures were high enough to completely melt both iron and silicate materials, the process resembled the separation of immiscible liquids, with dense metallic melts settling through lighter silicate liquids under the influence of gravity, like oil settling through water, but operating in reverse due to the inverted density relationship. Where only iron had melted while silicates remained solid, migration occurred through percolation. Liquid metal moved through networks of grain boundaries and pore spaces in the partially molten or solid silicate matrix, analogous to how water percolates through soil, but operating under extreme conditions of temperature and pressure that created chemical environments unlike anything found on Earth's surface today. In regions where both iron and silicates remained largely solid, segregation occurred through the formation of iron-rich diapirs, gravitationally unstable configurations where dense metallic material overlaid lighter silicates, eventually triggering the formation of descending columns of iron-rich material that would sink through the mantle toward the core, leaving behind iron-depleted regions in the upper portions of the planet. The energy released during core formation was staggering, equivalent to raising the average temperature of the entire planet by several thousand degrees Celsius. This wasn't just local heating around the segregating iron, it established Earth's thermal structure for billions of years to come, creating the temperature gradients that would drive convective motions in both the core and mantle and power geological processes that continue to operate today. The differentiated structure that emerged from this process established the fundamental framework for all subsequent geological evolution on Earth. The iron-nickel core, with a radius of approximately 3,485 kilometers, contains about 32% of Earth's mass, despite occupying only 16% of its volume, reflecting the extreme density of metallic materials under the high pressures that exist at the planet's center. Perhaps the most crucial consequence of core formation was the establishment of Earth's magnetic field through convective motion in the liquid outer core. The core, being composed of denser materials and receiving heat from both radioactive decay and the continued crystallization of the inner core, became a long-lived heat source that drives convective motions of electrically conductive liquid iron, generating Earth's magnetic field through the geodynamo process. This magnetic field extends far beyond Earth's surface, creating a protective magnetosphere that deflects most of the charged particles in the solar wind and prevents them from stripping away the planet's atmosphere. Without this magnetic shield, Earth would likely have lost its atmosphere to space over geological time, making it uninhabitable for life as we know it, much as appears to have happened to Mars after its magnetic field weakened and eventually disappeared. The chemical separation achieved during differentiation also established distinct reservoirs of elements that enable the rich diversity of geological processes that characterize Earth's surface. The preferential extraction of metallic iron left the mantle enriched in lighter elements, creating the compositional differences that drive mantle convection and plate tectonics, power volcanic activity and mountain building, and enable the continuous recycling of crustal materials that makes Earth a dynamic, evolving planet. The iron catastrophe thus represents far more than simply a rearrangement of Earth's internal structure. It was the foundational event that transformed a relatively simple, homogeneous planetary body into the complex, dynamic system capable of supporting the geological processes that make Earth habitable, protecting the atmosphere through magnetic shielding, and providing the energy sources that continue to drive planetary evolution after more than 4 billion years. Water. It covers 71% of Earth's surface, makes up 60% of your body, and is absolutely essential for every form of life we know. But here's something that will blow your mind. Virtually every drop of water on Earth had to be delivered after our planet formed. The moon-forming impact had vaporized any water present during Earth's initial assembly, meaning our entire ocean had to be rebuilt from cosmic deliveries and internal outgassing over hundreds of millions of years. Following the giant impact, Earth's surface was far too hot for liquid water to exist anywhere on the planet. Surface temperatures exceeded 1200 degrees, and the atmosphere consisted of superheated steam and vaporized rock that created conditions where water could only exist as a gas, and much of that water vapor was likely lost to space due to the extreme energy environment. This meant that virtually all of Earth's current water inventory had to be acquired through processes that operated after the planet's initial formation. The delivery of water to early Earth occurred through three primary mechanisms, each operating simultaneously but with varying degrees of importance over different periods of planetary evolution. The first, and initially most significant source, was volcanic outgassing from the planet's interior, where water vapor that had been trapped within silicate minerals during Earth's accretion was released through intense volcanic activity as the planet's interior began to differentiate and convect. This water had originally been incorporated into Earth's building materials as hydroxyl groups bound within the crystal structures of hydrous minerals, particularly in materials similar to carbonaceous chondrite meteorites that contain significant quantities of water locked within their rocky matrices. As Earth's interior heated up due to radioactive decay and gravitational contraction, these as minerals underwent dehydration reactions that released enormous quantities of water vapor into the atmosphere through volcanic eruptions and outgassing processes. Volcanic outgassing during the Hadean Eon was extraordinarily vigorous, with water vapor constituting approximately 80% by volume of the gases released during volcanic eruptions, far exceeding the proportion found in modern volcanic emissions. This water vapor, along with carbon dioxide, sulfur dioxide, nitrogen, and other gases, began to accumulate in Earth's atmosphere as the planet gradually cooled, following the initial period of intense bombardment. The second major source of water delivery came from the continued bombardment of Earth by asteroids and comets during the late heavy bombardment period, when gravitational perturbations from the migrating giant planets scattered countless icy objects from the outer solar system throughout the inner solar system. These impact events delivered enormous quantities of water ice that had been preserved in the cold outer regions of the solar system since the formation of the protoplanetary disk. Recent research using isotopic fingerprints has revealed important insights into the relative contributions of different types of extraterrestrial objects to Earth's water inventory. The ratio of deuterium to hydrogen serves as a cosmic fingerprint for identifying the source regions of water throughout the solar system. Comets from the outer solar system have deuterium to hydrogen ratios approximately twice that of Earth's oceans, suggesting that traditional comets could have contributed at most 10% of Earth's total water inventory. However, asteroids, particularly those from the outer regions of the asteroid belt between Mars and Jupiter, appear to have been more important contributors than previously recognized. Analysis of samples returned from asteroids Ryugu and Bennu has revealed that these objects contain water with isotopic signatures closely matching Earth's oceans, suggesting that asteroid impacts could have delivered a significant fraction of the water in Earth's oceans. The third and perhaps most surprising potential source of Earth's water has emerged from recent research suggesting that much of our planet's water may have been present from the very beginning, incorporated into the rocky materials from which Earth formed rather than delivered by later impacts. Studies of enstatite chondrite meteorites, which are thought to represent the type of materials from which Earth accreted, have revealed that these rocks contain sufficient hydrogen bound within their mineral structures to account for at least 3 times the mass of water in Earth's current oceans. The transition from water vapor in the atmosphere to liquid water on Earth's surface marked one of the most critical thresholds in planetary evolution, occurring when surface temperatures finally dropped below the critical point of water around 374 degrees Celsius, approximately 3.8 billion years ago. This cooling was facilitated by the gradual decline in impact heating as the late heavy bombardment waned, the loss of atmospheric heat to space as the rock vapor atmosphere finally condensed and precipitated out, and the beginning of carbon dioxide removal from the atmosphere through dissolution in liquid water. The first rainfall on Earth would have been unlike anything experienced in recorded history, with some models suggesting that the initial condensation events may have involved continuous precipitation for centuries or even millennia, as the enormous inventory of atmospheric water vapor gradually condensed and collected in the lowest elevations of Earth's surface. These early rains were highly acidic due to the large quantities of sulfur dioxide, hydrogen sulfide, and other volcanic gases dissolved in the atmospheric water vapor, creating conditions that would have been extremely corrosive and chemically reactive. The early oceans that formed through this process were fundamentally different from modern seawater in both their chemical composition and physical properties. These primordial waters were highly acidic, with pH values possibly as low as 1 or 2, and contained much higher concentrations of dissolved metals, sulfur compounds, and other chemicals leached from the newly formed crustal rocks. The water temperature was also much higher than in modern oceans, with surface temperatures potentially exceeding 70 degrees Celsius due to the intense greenhouse effect created by the carbon dioxide-rich atmosphere. The establishment of stable liquid water on Earth's surface enabled the beginning of more complex chemical processes that would prove essential for the eventual emergence of life. The interaction between liquid water and the mineral surfaces of early crustal rocks initiated weathering processes that began to modify both the composition of the oceans and the chemical evolution of the atmosphere, while the presence of liquid water enabled the concentration and chemical modification of organic compounds that may have been delivered by meteorites and comets. Every drop of water in today's oceans, lakes, and rivers represents a tangible connection to this ancient process of cosmic delivery and planetary evolution, making the story of Earth's water one of the most remarkable examples of how the most essential requirements for life can emerge from the most unlikely and violent cosmic circumstances, transforming our plan. From a sterile, rocky world into a dynamic, potentially habitable environment where complex chemistry could operate and life could eventually emerge. Hidden within crystals smaller than grains of sand lie the secrets of Earth's greatest revolution, the emergence of plate tectonics that transformed our planet from a static, stagnant world into the dynamic, self-renewing system we see today. These nearly indestructible zircons formed 3.8 billion years ago in the Barberton Greenstone Belt of South Africa, contain chemical fingerprints that reveal when Earth became unique among rocky planets through the development of the geological processes that continue to shape our world. For the first billion years of Earth's existence, our planet's surface was largely static, resembling Mars or Venus today, with a single, unbroken crustal shell covering a slowly cooling interior. But approximately 3.8 billion years ago, something extraordinary happened that would distinguish Earth from every other rocky planet in our solar system. The birth of plate tectonics, a revolutionary development that changed everything about how our planet operates. The evidence comes from some of the most sophisticated geological detective work ever undertaken, involving the analysis of microscopic zircon crystals that have survived for nearly 4 billion years as tiny time capsules preserving the chemical signatures of their formation environments. These zircons contain isotopic and trace element evidence that points to their formation in subduction zones, the characteristic environments where one tectonic plate slides beneath another, creating the high-pressure conditions necessary for generating the distinctive chemical signatures found in these ancient gems. Recent breakthrough research using quantum diamond microscopy has found evidence for continental drift rates of 2.5 centimeters per year in 3.2 billion-year-old rocks from Western Australia, remarkably similar to modern plate velocities. This evidence comes from the analysis of magnetic minerals within ancient volcanic rocks that preserved records of changes in Earth's magnetic field orientation as the rocks moved across the planet's surface, providing a kind of geological GPS system that allows scientists to track the motion of ancient crustal fragments. The physical mechanism underlying this tectonic revolution involved the gradual cooling and strengthening of Earth's lithosphere, the rigid outer shell composed of the crust and uppermost mantle, until it became sufficiently strong and brittle to fracture into discrete plates capable of moving independently across the planet's surface. During Earth's earliest history, The combination of intense internal heating from radioactive decay and continued bombardment had maintained the lithosphere in a hot, weak, and ductile state that could not support the rigid plate behavior necessary for true plate tectonics. The initiation of plate tectonics required not only the physical strengthening of the lithosphere, but also the development of sufficient density contrasts between different types of crustal material to drive the process of subduction, the sinking of dense oceanic crust beneath lighter continental crust that represents the fundamental driving mechanism of plate motion. The formation of the first substantial volumes of continental crust during the early Archean period created these essential density contrasts through the partial melting of hydrated oceanic basalts under high-pressure conditions. The establishment of plate tectonics triggered a cascade of interconnected changes that transformed Earth's surface environment in ways that would prove essential for the eventual emergence and evolution of life. The process of subduction began to recycle oceanic crust back into the mantle, carrying with it sediments and seawater that had accumulated on the ocean floor, thereby initiating the complex geochemie, cycles that regulate the composition of the atmosphere and oceans over geological timescales. One of the most significant consequences of the tectonic revolution was the establishment of the carbon cycle as a long-term climate regulatory mechanism, fundamentally altering Earth's ability to maintain stable surface temperatures over billions of years. The process of subduction began to transport carbon-bearing sediments and altered oceanic crust into the mantle, where they would be heated and partially melted, releasing carbon dioxide back to the atmosphere through volcanic emissions at convergent plate boundaries. The emergence of plate tectonics also played a crucial role in generating the first substantial land masses and establishing the basic geography that would influence global climate patterns for billions of years to come. The collision and accretion of smaller crustal fragments during the Archean period gradually assembled the first large continental masses, while the opening and closing of ocean basins through the processes of seafloor spreading and subduction began to influence oceanic circulation patterns and heat transport around the globe. Recent research has revealed evidence for some of Earth's earliest great earthquakes preserved in the 3.3 billion-year-old geological record, providing direct evidence for the violent seismic activity that characterizes active plate boundaries and demonstrating that the fundamental physical processes of plate tectonics, including the sudden release of accumulated tectonic stress through brittle failure of crustal rocks, were already operating with remarkable effectiveness during Earth's youth. The tectonic revolution also established the mechanisms by which Earth's magnetic field could be sustained over geological timescales, as the convective motions in the liquid outer core that generate the planet's magnetic field are intimately connected to the thermal structure of the mantle, which in turn is strongly influenced by the patterns of heat transport established by plate tectonics. The magnetic field generated by these processes provides essential protection for the atmosphere and surface environment from the charged particles of the solar wind. The establishment of plate tectonics during the Archean period thus represents far more than simply the beginning of continental drift. It marked the emergence of Earth as a truly dynamic, self-regulating planetary system capable of maintaining the complex environmental conditions necessary for life. The intricate feedbacks between tectonic processes, atmospheric composition, ocean chemistry, and climate regulation that were established during this period continue to operate today, making plate tectonics one of the fundamental characteristics that distinguishes Earth from other rocky planets in the solar system and establishes the geological framework that would eventually make complex life possible. 4 billion years ago, Earth became the stage for the greatest chemistry experiment in the solar system. With tectonic activity creating diverse environments, liquid water providing a universal solvent, and energy sources ranging from volcanic heat to lightning strikes, our planet began mixing elements in ways that had never occurred before, setting up the chemical pathways that would eventually create life itself in a process that transformed our world from a sterile, rocky planet to one capable of supporting the complex biochemical processes that characterize all known life. The chemical theater was set by Earth's fundamentally reducing atmosphere, markedly different from today's oxygen-rich environment. Composed primarily of carbon dioxide, nitrogen, water vapor, methane, and ammonia. This atmosphere created conditions that were chemically favorable for the synthesis of organic compounds from simple inorganic precursors through reactions that would be impossible in our current oxidizing environment. This reducing nature was maintained by continuous volcanic outgassing from the planet's interior, which released enormous quantities of hydrogen-rich gases that scavenged any free oxygen that might have been produced through the photodissociation of water vapor. Recent research has revealed that natural radioactivity played a crucial role in driving early chemical transformations, with the decay of radioactive isotopes in the global ocean initiating extensive chemical reactions that promoted both the formation of organic matter and the gradual purification of seawater from toxic compounds. The decay of radioactive isotopes created reducing agents and energy sources that powered organic synthesis reactions on a planetary scale, transforming what might have been a chaotic mixture of simple chemicals into increasingly organized molecular systems. The synthesis of organic compounds on early Earth operated through multiple pathways simultaneously, creating a diverse and dynamic chemical environment that bears little resemblance to the simple primordial soup often portrayed in popular scientific literature. Atmospheric chemistry driven by ultraviolet radiation, electrical discharges from lightning, and shock waves from meteorite impacts provided one major source of organic molecules, producing amino acids, nucleotide bases, and other biologically relevant compounds through gas phase reactions in the reducing atmosphere. These atmospheric synthesis products would rain down into the oceans and accumulate in freshwater pools, where they could undergo further chemical processing and concentration. However, the terrestrial production of organic compounds was complemented by significant extraterrestrial delivery through the continued bombardment of Earth by comets, asteroids, and interplanetary dust particles that carried rich cargoes of organic molecules synthesized in the cold outer regions of the solar system. Perhaps the most significant breakthrough in understanding early Earth's chemistry has come from the recognition that hydrothermal vents served as natural laboratories for prebiotic chemistry on a massive scale. These underwater geysers, where superheated mineral-rich water emerges from the sea floor, created unique chemical microenvironments where the reducing chemistry necessary for organic synthesis could operate even more efficiently than in the atmosphere or open ocean. The process of serpentinization, where seawater reacts with ultramafic rocks such as olivine, produces large volumes of hydrogen gas while creating alkaline conditions ideal for the formation of organic compounds. When these warm, hydrogen-rich fluids mix with the iron-rich waters of the early ocean, they create chemical gradients and catalytic mineral surfaces that can drive the synthesis of increasingly complex organic molecules, including the amino acids, nucleotides, and lipids that form the basic building blocks of all known life. Recent discoveries have revealed that ancient hydrothermal vents supplied trillions of tiny, highly reactive particles of the mineral greenolite, along with large quantities of phosphorus-bearing apatite, into Earth's early oceans. These microscopic mineral particles, measuring only a few hundred nanometers across, could be transported thousands of kilometers by ocean currents, potentially seeding diverse environments with the catalytic surfaces necessary to promote otherwise unfavorable chemical reactions. The chemical environment of early Earth's oceans was characterized by conditions that modern life would find extremely hostile. Yet these same conditions proved essential for driving the complex chemistry that would eventually lead to biological systems. The early oceans were highly acidic, with pH values potentially as low as 1 or 2, due to large quantities of sulfur dioxide and other volcanic gases dissolved in the water, and they contained much higher concentrations of dissolved metals that could serve as catalysts for organic synthesis reactions. Recent experimental work has demonstrated that when organic mixtures are subjected to the wet-dry cycles that would have been common on early Earth, the resulting chemistry is far from chaotic. Instead of producing random molecular mixtures, these wet-dry cycles drive continuous transformation, selective organization, and synchronized population dynamics among organic molecules, creating conditions that favor the formation of increasingly complex molecular assemblages while simultaneously removing less stable compounds from the system. The emergence of self-replicating molecules represents perhaps the most crucial transition in the chemistry of early Earth, marking the point where purely chemical processes began to exhibit the characteristics we associate with biological evolution. The leading hypothesis for this trend is Eon involves the formation of RNA molecules capable of catalyzing their own replication, creating an RNA world where these versatile molecules served simultaneously as genetic material, catalysts, and structural components of primitive cells. The development of primitive metabolic pathways represents another crucial aspect of early Earth's chemical evolution, establishing the energy harvesting and biosynthetic processes that would eventually become central to all living systems. The earliest metabolic pathways likely involved simple redox reactions between inorganic compounds, such as the reaction between hydrogen and carbon dioxide to form organic acids and alcohols, or the reduction of sulfate to hydrogen sulfide coupled with the oxidation of organic matter. The transition from individual organic molecules to organized cellular systems required the development of compartmentalization mechanisms that could concentrate reactants, exclude harmful compounds, and maintain the chemical gradients necessary for energy storage and utilization. The formation of the first cell membranes likely involved amphipathic molecules that spontaneously assemble into bilayer structures when placed in aqueous solutions, creating the first protocells that could maintain their own chemical environment while exchanging materials and energy with their surroundings. The chemistry of early Earth's transition to a living world represents one of the most remarkable examples of emergent complexity in the natural world, where simple inorganic compounds were transformed through purely physical and chemical processes into the sophisticated molecular machinery that characterizes all known life, requiring the convergence of favorable environmental conditions, diverse energy sources, appropriate catalytic surfaces, and the intrinsic self-organizing properties of carbon-based chemistry operating over hundreds of millions of years. The oxygen revolution represents one of the most catastrophic and transformative events in Earth's evolutionary history, fundamentally altering the planet's atmospheric composition, environmental chemistry, and the trajectory of life itself. This extraordinary transformation, occurring approximately 2.4 billion years ago during the Paleoproterozoic era, marks the moment when Earth's atmosphere shifted from a reducing, oxygen-poor environment to an oxidizing one that would eventually support the complex life forms we see today, representing a profound example of how life itself can become a geological force capable of reshaping planetary environments. The primary architects of this atmospheric revolution were microscopic organisms called cyanobacteria, which had evolved the remarkable ability to harness solar energy through oxygenic photosynthesis, a process that used sunlight, carbon dioxide, and water to produce organic compounds while releasing molecular oxygen as a waste product. These blue-green microorganisms, whose photosynthetic machinery would eventually give rise to the chloroplasts found in all modern plants, represented one of the most significant biological innovations in Earth's history and would fundamentally change the planet's environmental trajectory. Prior to their emergence, Earth's atmosphere contained virtually no free oxygen, instead being dominated by carbon dioxide, nitrogen, methane, and other reducing gases that created conditions similar to those found today on Venus and Mars. The early atmosphere was fundamentally incompatible with oxygen-dependent life forms, as free oxygen was rapidly consumed by reactions with abundant reducing compounds such as hydrogen sulfide, methane, and particularly ferrous iron, dissolved in the oceans. For hundreds of millions of years following the evolution of oxygenic photosynthesis, the oxygen produced by cyanobacteria was immediately consumed by chemical reactions with the vast reservoirs of reduced compounds that characterized early Earth's surface environment. The most significant of these oxygen sinks was the enormous quantity of dissolved ferrous iron in the oceans, which reacted with oxygen to form ferric iron oxides that precipitated out of solution as distinctive layered deposits known as banded iron formations. These remarkable geological structures, which represent some of the world's most important iron ore deposits, provide a vivid record of the gradual oxygenation of Earth's oceans and serve as a kind of geological barometer for tracking the rise of atmospheric oxygen levels. As long as ferrous iron remained abundant in the oceans, any oxygen produced by photosynthesis would be quickly consumed, preventing its accumulation in the atmosphere and maintaining Earth in its primordial oxygen-free state. The transition from an oxygen sink-dominated system to one where oxygen could begin accumulating in the atmosphere required reaching a critical threshold where the rate of oxygen production finally exceeded the capacity of reducing compounds to consume it. This tipping point was reached through a complex interplay of biological, geological, and environmental factors that gradually shifted the balance in favor of oxygen accumulation, including the burial of organic carbon in sediments and changes in volcanic outgassing patterns. The consequences of oxygen accumulation were immediate, dramatic, and paradoxical in their effects on Earth's biosphere and climate system. The rise of atmospheric oxygen triggered what may have been the most severe mass extinction in Earth's history, devastating the anaerobic microbial communities that had dominated the planet for over 1 billion years. These organisms, which had evolved sophisticated metabolic pathways adapted to oxygen photos, conditions, suddenly found themselves in an environment where their cellular machinery was under constant attack by highly reactive oxygen molecules. Simultaneously, the accumulation of oxygen in the atmosphere initiated a cascade of chemical reactions that profoundly altered Earth's climate system and set the stage for one of the most extreme climate events in planetary history: the oxidation of atmospheric methane, a potent greenhouse gas that had helped maintain warm global temperatures despite the young sun's lower luminosity, to carbon dioxide and water vapor, dramatically reduced the greenhouse effect and triggered a period of severe global cooling, known as the Huronian glaciation. The formation of the ozone layer represents another crucial consequence of atmospheric oxygenation that would prove essential for the eventual colonization of Earth's surface by complex life forms. As oxygen accumulated in the atmosphere, some of it was converted to ozone through reactions driven by solar ultraviolet radiation, creating a protective layer in the stratosphere that began to absorb much of the harmful ultraviolet radiation that had previously sterilized the planet's surface. Prior to ozone layer formation, life was restricted to underwater environments or other locations where water or rock could provide protection from the lethal levels of UV radiation reaching Earth's surface. The development of this protective ozone shield was therefore a prerequisite for life's eventual expansion onto land, making it one of the most important atmospheric developments in the history of biological evolution. The chemical transformation of Earth's surface environment during the oxygen revolution triggered an unprecedented explosion in mineral diversity that fundamentally altered the planet's geological character. Prior to atmospheric oxygenation, Earth's surface was dominated by reduced mineral phases that formed under oxygen-poor conditions, but the introduction of free oxygen created an entirely new chemical environment where oxidized minerals could form for the first time, leading to the emergence of more than 2,500 new mineral species. The long-term biological consequences of the oxygen revolution were equally profound, setting the stage for the evolution of eukaryotic cells and eventually complex multicellular life. The availability of free oxygen enabled the evolution of aerobic respiration, a metabolic process that extracts far more energy from organic compounds than the anaerobic pathways that had dominated early life, providing the enhanced energy budget that would eventually enable the evolution of large, complex cells and multicellular organisms. Recent research has revealed that the oxygen revolution was not a simple, monotonic increase in atmospheric oxygen levels, but rather a complex process involving multiple phases of oxygenation separated by periods of stagnation or even decline, demonstrating that the transition to an oxygenated world was neither inevitable nor permanent, but rather the result of a delicate balance between competing biological and geochemical processes. The oxygen revolution thus represents far more than simply the introduction of a new atmospheric component. It was a comprehensive transformation of Earth's environmental system that reset virtually every aspect of planetary evolution and established the chemical and biological framework within which all subsequent life would evolve, demonstrating the profound capacity of life to modify planetary environments and showing how biological innovations can trigger cascading changes that alter atmospheric composition, climate systems, and the very foundations of ecological organization. The modern Earth Awakens represents the culmination of billions of years of planetary evolution, encompassing the final major transformative events that shaped our world into the dynamic, complex system capable of supporting the rich diversity of life we see today. This remarkable period, spanning approximately the last 750 million years, witnessed some of the most dramatic and consequential changes in Earth's environmental system since the origin of oxygenic photosynthesis, including extreme climate oscillations that pushed the planet to its physical limits and the revolutionary biological innovations that established entirely new forms of life. The snowball Earth events of the Neo-Proterozoic era, occurring between approximately 750 and 635 million years ago, represent perhaps the most extreme climate episodes in Earth's entire history, when glacial ice extended from the poles to the equator and potentially encased the entire planet in a frozen shell up to a kilometer thick. These global glaciation events were triggered by a complex interplay of factors, including the arrangement of continents around the equator, which enhanced weathering of silicate rocks and removed carbon dioxide from the atmosphere, leading to runaway cooling as the planet's reflective ice surface created a positive feedback loop. The severity of these ice ages was so extreme that they threatened to extinguish most life on Earth, creating conditions more hostile than anything experienced during the subsequent history of complex life. Yet paradoxically, these near-extinction events may have been the crucial catalyst that drove the evolution of the first complex multicellular organisms through mechanisms that scientists are only beginning to understand, as the extreme environmental stress created selective pressures that favored organisms capable of surviving harsh, oxygen-poor conditions beneath kilometers of ice. Research suggests that the physical constraints imposed by the ice-covered world gave multicellular eukaryotes significant evolutionary advantages over their simpler single-celled predecessors, as multicellular organisms could better cope with limited resources through cellular specialization and cooperative strategies. Additionally, the snowball Earth periods were associated with dramatic increases in phosphorus availability in the oceans, potentially reaching levels several times higher than usual, and providing the essential nutrients needed to support more complex life forms once the ice began to melt. The continental configuration changes that occurred throughout the later Precambrian and Phanerozoic eons profoundly influenced global climate patterns and ocean circulation systems, establishing the geographical framework within which modern life would evolve and diversify. The gradual assembly and subsequent breakup of supercontinents like Pannotia and Pangaea created dramatic shifts in atmospheric and oceanic circulation patterns that influenced everything from regional weather patterns to the global distribution of heat and nutrients. Perhaps the most consequential of these geographical changes was the formation of the Isthmus of Panama approximately 3 million years ago, which closed the oceanic connection between the Atlantic and Pacific Oceans, fundamentally altered global ocean circulation patterns, and contributed to the onset of the Pleistocene ice ages that would dominate Earth's recent climate history. These continental rearrangements not only influenced climate, but also created new opportunities for biological evolution. By isolating populations on different continents and periodically reconnecting previously separated biogeographic regions, the emergence of complex multicellular life represents one of the most profound transitions in the history of biology, marking the point when simple single-celled organisms began to cooperate and specialize to form the elaborate body plans that characterize modern plants and animals. Recent research has pushed the timeline for complex multicellularity much further back in Earth's history than previously thought, with evidence suggesting that sophisticated multicellular eukaryotes existed as early as 1.6 billion years ago, some 600 million years earlier than traditionally believed. These ancient organisms exhibited key characteristics of complex multicellularity, including cell-to-cell adhesion, cellular differentiation, and programmed cell death, demonstrating that the fundamental innovations underlying modern plant and animal life were established long before the famous Cambrian explosion. The transition to multicellularity was not a single evolutionary event, but rather a gradual process that occurred multiple times in different lineages, ultimately culminating in the diverse array of body plans that emerged during the Ediacaran period. The Pleistocene epoch beginning approximately 2.6 million years ago, ushered in a new phase of Earth's climate history characterized by dramatic oscillations between ice ages and warm interglacial periods that profoundly influenced the evolution and distribution of life, particularly the emergence and expansion of human civilization. These ice age cycles, driven by subtle variations in Earth's orbital parameters, created a rapidly changing environment that favored organisms capable of adapting quickly to shifting conditions. The expansion and contraction of continental ice sheets not only influenced global sea levels and climate patterns, but also created land bridges and barriers that facilitated or prevented the migration of species between different continents, leading to dramatic biogeographic reorganizations that shaped the modern distribution of plant and animal life. During glacial periods, vast quantities of water were locked up in continental ice sheets, lowering sea levels by up to 120 meters and exposing land bridges such as Beringia between Asia and North America. The emergence of humans as a geological force represents the most recent and perhaps most dramatic chapter in Earth's evolutionary history, marking the point when a single species became capable of influencing planetary-scale environmental processes with a speed and magnitude comparable to major geological events. Human influence on Earth's surface environment began much earlier than traditionally recognized, with archaeological evidence suggesting that farming, pastoralism, and even hunter-gatherer activities had created significant landscape modifications by 4,000 years ago. The development of agriculture fundamentally altered Earth's surface by converting natural ecosystems into managed landscapes, changing patterns of erosion and sedimentation, and initiating the large-scale movement of species between continents. However, the pace and scale of human environmental impact accelerated dramatically during the industrial era, as the burning of fossil fuels, the development of synthetic chemicals, and the exponential growth of human populations created environmental changes that operate on timescales much faster than natural geological processes. The modern human impact on Earth's environmental systems has become so pervasive and significant that many scientists now argue we have entered a new geological epoch, the Anthropocene, characterized by human activities as the dominant influence on climate, atmospheric composition, biodiversity, and surface processes. This human influence operates through numerous mechanisms, including the emission of greenhouse gases, the modification of biogeochemical cycles, the acceleration of species extinctions, and the physical restructuring of Earth's surface through mining, urbanization, and agriculture. The modern Earth awakens. Thus represents far more than simply the final chapter in a long geological story. It marks the transition from a planet shaped purely by natural processes to one where the future evolution of environmental systems depends critically on the actions and decisions of a single species that has become a geological force in its own right, demonstrating how the most recent phases of Earth's evolution have been characterized by accelerating complexity and increasingly rapid rates of change that continue to shape our planet's future. Earth's cosmic significance represents the grand finale of our extraordinary 4.6 billion-year journey, revealing how our planet's transformation from cosmic dust to a living world provides profound insights into planetary science, astrobiology, and humanity's ongoing search for life throughout the universe. The significance of Earth's formation story extends far beyond our own planet, serving as both a template for understanding rocky planet evolution across the cosmos and a crucial reference point for evaluating the habitability of the thousands of exoplanets now being discovered around distant stars. Recent groundbreaking discoveries have fundamentally challenged our understanding of Earth's earliest development, with new research revealing that our planet's continental crust formation occurred billions of years earlier than previously thought, completely revolutionizing theories about when the conditions necessary for life could have first emerged. Computer models simulating Earth's formation have revealed that the protocrust, the planet's very first solid surface, would naturally have developed chemical characteristics remarkably similar to modern continents without requiring the complex plate tectonic processes that scientists had assumed were essential for creating habitable conditions. This dramatic revision of Earth's timeline has profound implications not only for understanding our own planet's history, but also for assessing the potential habitability of other worlds, suggesting that the complex geological processes necessary for supporting life may develop much more rapidly and efficiently than scientists had previously imagined. The discovery that Earth's continental signatures emerged so early in planetary history suggests that the geological processes necessary for long-term climate regulation and the concentration of essential elements for life may develop much more readily than previously assumed, potentially making habitable conditions more common throughout the universe than current estimates suggest. The template that Earth provides for understanding planetary formation has become increasingly important as astronomers have discovered more than 5,000 confirmed exoplanets orbiting distant stars, with many showing characteristics that could potentially support liquid water and life as we know it. Earth's formation story demonstrates the remarkable sequence of cosmic coincidences and physical processes that must align to create a habitable world. The right distance from a stable star to maintain liquid water, a substantial magnetic field to protect the atmosphere from stellar winds, plate tectonics to regulate climate and recycle essential elements, and the proper mix of volatile compounds delivered through impacts and outgassing. Yet Earth's story is also a testament to extraordinary cosmic chance and the delicate balance of factors that made our world uniquely hospitable. The giant impact that formed our moon was not just a destructive collision, but a transformative event that stabilized Earth's axial tilt, creating the seasonal variations that drive climate diversity and may have been essential for the evolution of complex life. The presence of plate tectonics on Earth appears crucial for maintaining long-term habitability by regulating atmospheric composition through the carbon cycle. Yet this process may be relatively uncommon among rocky planets, as evidenced by the apparently static surfaces of Mars and Venus. The ongoing exploration of exoplanets through increasingly sophisticated telescopes and space missions is revealing worlds of incredible diversity, some rocky and Earth-like, others gaseous giants, some shrouded in thick atmospheres, others heartbreakingly dry and barren. As our observational tools become more powerful, particularly with missions like the James Webb Space Telescope probing planetary atmospheres for signs of water vapor, oxygen, and other potential biosignatures, we edge ever closer to answering one of humanity's most profound questions. Are we alone in the universe? The comparative study of planetary evolution has revealed that Earth's development was shaped by a remarkable series of fortuitous circumstances that may be relatively rare in the universe, including not only the moon-forming impact, but also the timing of water delivery, the emergence of plate tectonics, and the evolution of photosynthetic life that created our oxygen-rich atmosphere. Understanding why Earth developed and maintained these life-supporting characteristics, while its planetary neighbors did not, remains one of the most important questions in planetary science, with profound implications for assessing the habitability of Earth-like exoplanets around other stars. The search for habitable exoplanets has been guided primarily by Earth-based criteria, focusing on rocky worlds orbiting within their star's habitable zone, where temperatures allow liquid water to exist. But Earth's formation story reveals that habitability depends on an intricate web of interconnected processes involving planetary size, internal structure, atmospheric evolution, impact history, and the timing of various geological and biological innovations. The discovery that Earth's continental signatures emerged so early suggests that the geological framework for habitability may develop more readily than previously assumed, potentially expanding the number of worlds that could support life. Looking toward the future, Earth's formation story provides both a roadmap and a cautionary tale for humanity's role as stewards of planetary environments, demonstrating how biological processes can become geological forces capable of fundamentally altering atmospheric composition and global climate systems. The oxygen revolution that occurred 2.4 billion years ago shows how the emergence of new biological processes can trigger global environmental changes that persist for billions of years, while the more recent emergence of human civilization demonstrates how intelligent life can become a geological force operating on timescales much faster than natural processes. As we continue to discover new worlds around distant stars and develop increasingly sophisticated techniques for studying their characteristics, Earth's formation story will remain the fundamental reference point for understanding what makes planets habitable, how life can emerge from non-living matter, and whether the extraordinary sequence of events that led to our existence represents a common pathway in cosmic evolution or a remarkable cosmic accident that may be unique in the observable universe. The cosmic significance of Earth's formation thus extends far beyond its value as a case study in planetary science, representing a profound meditation on the nature of complexity, the role of contingency in natural systems, and the remarkable capacity of simple physical processes to generate the conditions necessary for life, intelligence, and technological civilization. The story of how cosmic dust became a living world reveals the interconnected nature of astronomical, geological, and biological processes operating across vast scales of space and time, demonstrating that understanding our place in the universe requires integrating knowledge from fields ranging from stellar astrophysics and planetary dynamics to geochemistry, evolutionary biology, and climate science. So as we reach the end of our cosmic journey tonight, let your mind wander through the vast expanse of time and space that brought this pale blue dot to life. From the first whisper of matter in an ancient stellar nursery, through violent collisions that forged our moon, across eons of chemical evolution that sparked the first life, to the emergence of consciousness capable of understanding its own origins, Earth's story is ultimately the story of us all. In understanding how our planet came to exist, we begin to understand ourselves and our extraordinary place in the infinite cosmos. Sweet dreams, fellow travelers through deep time, and remember, you are made of star stuff, living on a world that defied impossible odds to become the most precious thing we know, home.